Welcome back to the final section of Chapter 10. If you notice, we skipped 10.3. If I'm being honest, I can't remember exactly what the title of that is in the textbook, but we don't cover that. So we are going to head right on over to analyzing dependent samples. So in 10.2, we looked at two groups and we were comparing the means of those two groups. In 10.4, we're still dealing with means, but we are conducting what's called a paired t-test. And this would be a hypothesis test for two dependent means. So in 10.2, the two groups that we were comparing were independent from one another. But in a paired t-test, the two groups are dependent. So some examples might include these three bullets that I have here. So the before and after effect of a pharmaceutical treatment on the same group of people. So if a group of people takes this treatment and we measure their response before and after the treatment, we would want to make sure that we compare pre and post for the same person. It wouldn't make sense to compare my pre with your post. So we want to make sure that we pair those two observations together because they're dependent on the person. Body temperature using two different thermometers on the same group of participants. Same thing. Each of us have a kind of normal body temperature. I know the norm is supposed to be 98.6, but not all of us have that exact 98.6. But if we're comparing two different thermometers, we want to make sure we compare thermometer 1 on person 1 and then thermometer 2 on person 1 as well, instead of doing thermometer 1 on me and thermometer 2 on you, because me and you are different and there's going to be some just internal variation from person to person. So we want to make sure that we look at the two observations that are dependent on each person. So thermometer 1 with me, thermometer 2 with me, thermometer 1 on you, thermometer 2 on you. So we're pairing together two observations and they depend on something, generally a person. The last one, standardized test results of a group of students before and after a study prep course. So again, we don't want to just look at all the pre-test scores and all the post-test scores. Those two groups aren't independent of one another. If I am just a bad test taker, I might do poorly on both the pre-test and the post-test, or this before test and this after test, right? So we want to compare the differences. So we would want to look at my pre-test and my post-test and see, was there an increase? Was there a decrease? Was there a difference of 0? Look at your pre-test, your post-test, and again, look to see what was your difference. So we want to pair those two observations, pre and post-test, together based on individual person. So they are dependent on the person that took them. So unfortunately, we can't actually do this experiment. I thought of ways to feasibly do this, and I couldn't figure out a way to make this work well. But here is the idea. I would have had us do an experiment to kind of see the difference between a two-sample t-test, that would be two independent samples, versus a paired t-test. So I'm just going to kind of talk us through this example and hopefully kind of give you a concrete context of why a paired t-test might be better than a two-sample t-test. So this one we are investigating are standing pulse rates generally higher than sitting pulse rates. So I want to compare two different experiments. So the first one, I want to do a two-sample t-test. That's on the left-hand side over here. And a two-sample t-test would be what we just talked about in 10.2. So in the two-sample t-test, we're going to have two independent groups, and we want to think about randomly assigning half of the group to sit and randomly assign the other half of the group to stand. So imagine we're all in our big classroom that we got to sit in for about half the semester, And I have you guys flip an imaginary coin. And if you get heads, then you have to sit. If you get tails, then you have to stand. Okay? So each of us are going to measure our pulse rate in a 30-second interval while we're sitting or standing, depending on which treatment you are assigned. And at the end, we're going to compare the average pulse rate of everyone that sat and the average pulse rate for everybody that stood. So I did make kind of a fake table of data so you can kind of see how the data would be organized. So for person 1, let's pretend that they got stand as their treatment, so we would record the pulse rate. Person 2, their treatment was sit, so we would record their pulse rate. So at the end of this, if we have 100 people, let's say 50 people hopefully were assigned to stand, or we could make it that way. 50 people were assigned to sit. So we would want to find the mean pulse rate for all 50 that stood, the mean pulse rate for all 50 that sat, and then compare X bar stand and X bar sit. So our null hypothesis would be something like mu stand minus mu sit equals 0. So that's what we're trying to make an inference about, the true mean pulse rate of those that stand minus the true mean pulse rate of those who sit. Okay, now let's talk about a paired t-test. So a different way to conduct this experiment would be to take pretend like we never did the 2-sample test. Okay, so let's pretend like we're doing a whole new experiment. So we're all sitting in the classroom. There's a ton of us in there. Let's assume there's 100 people in there. I'm going to ask everyone to flip a coin, and we're going to randomly assign half to sit and half to stand. So just like before, randomly assign half to sit, half to stand. Each person's going to measure their pulse rate, just like we did before, depending on which treatment you were assigned. We're going to allow some time to pass, maybe look at a different example, something like that. Then I'm going to have you guys measure your pulse rate again in the same 30-second interval, but with the opposite treatment you had before. Meaning, if you sat first, now you'll stand. If you stood first, now you'll sit. So each person then has 2 observations. They have their sitting pulse rate as well as their standing pulse rate, and the random aspect came from the order in which you received your treatment. So every person has 2 observations, whereas here, each person only had 1 observation. They only took their pulse rate once, and it was when they were either standing or sitting, but not both. So now this is the important part. Each person is going to calculate their difference in pulse rate. So because we're trying to investigate are standing pulse rates higher than sitting pulse rates, generally higher or on average higher, we're going to subtract standing minus sitting for every single person. So let's take a look at how I've organized my data table here. So again, we're pretending like we have 100 people. All 100 people stand and sit. It's just the order was randomized. So maybe you stood first and then sat, but maybe I sat first and then stood, right? So every single person 1 has a standing pulse rate and a sitting pulse rate. And then person 1 would subtract his or her standing minus sitting pulse rate to get this difference. Now, thinking about these differences here, those differences are either going to be positive, negative, or 0. Now, if we think that standing pulse rates are generally higher than sitting pulse rates, then we would want these differences to be positive. That would give us a good indication that on average, standing pulse rates are bigger or higher than sitting pulse rates. So what we're looking at now is not these individual groups here. What we care about is the difference. Now, the reason the difference is important is because this difference here is dependent on just person 1. So the reason this type of experiment for this context is better is because it's going to control the person-to-person variability in pulse rates. So I might naturally just have a high pulse rate. You might naturally just have a low pulse rate. So we want to look at the change in your pulse rate, even if they're 2 pretty low numbers. I don't know, maybe yours was 20 sitting and then 23 standing. So your difference, 23 minus 20, would be 3. It's still a positive difference. Whereas mine might be 36 and then 42, right? 42 minus 36, still a positive difference. So we want to control for the person-to-person variability. Otherwise, we're going to see a ton of overlap. So if I just plotted all of the standing pulse rates here, and then plotted all the sitting pulse rates and tried to see like overall where the standing dots higher, like if we're looking at a dot plot where the standing higher than the sitting, there's going to be so much overlap because there's so much variability in pulse rate from person to person. However, if we isolate that variability or control for that variability between person to person, and we look at your sitting, your standing, and only the difference, then if we make a dot plot of all those differences, if most of those differences are positive, then we do have pretty strong evidence that in general, standing pulse rates are in fact higher than sitting pulse rates. So I wanted to give you that context. I do wish that we could actually do the experiment, but I just could not figure out a feasible way to do that. But I want to talk about the data that you're actually using in your test. So in the 2-sample t-test, you're using the difference between 2 sample means. In your paired t-test, you're using the average of a bunch of differences. This is just a list of this is one list of numbers. Here we had a standing list of numbers and we found the average. We had a sitting list of numbers, we found the average, and now we're going to compare those two averages. Here, we're only dealing with one list of numbers as our data. So that's a very main difference between a 2-sample t-test and a paired t-test, which means our statistic is going to look a little bit different here. So we're looking at the average, so X bar, of a bunch of numbers that are differences. So that's what that little d stands for, differences. So we are making an inference about mu, the true mean of all of the differences. Had we done this experiment with many, many more people, or have we done this experiment with different groups of people? So the population of all differences, we want to know, is that mean 0? Is it bigger than 0? Is it smaller than 0? The same steps apply when we are looking at a hypothesis test or a confidence interval when we're looking at paired data. So our null hypothesis, as I stated earlier, our parameter of interest is the true mean, that's why we're using mu, of a bunch of differences. So the numbers that we're using as our data are numbers that are differences. So again, we've got the option of one-sided test versus a two-sided test. In 19, I asked us to state the hypotheses for the paired t-test that we just conducted kind of in the pulse rates example. So you do want to make sure you know which way you're subtracting, because that helps you figure out what your inequality symbol needs to be. So we were trying to answer the question, are standing pulse rates generally higher than sitting pulse rates? So I chose to subtract standing minus sitting, and if we think they're generally higher, or if we're trying to investigate that, then those differences, the average of all those differences, we would think should be positive. That would mean standing was higher than sitting. Again, we have our conditions, so our conditions here are very similar to the conditions we've seen before. This one is a big change. So we usually have an independence condition. This one is actually a dependence condition. So we need to make sure that we have dependent groups, and those groups are paired together. So standing observation with sitting observation, and it's paired based on person. So person 1 stood, person 1 sat. So person 1 has 2 pulse rates, and we pair those pulse rates together to find the difference. The other thing I want to mention here is that we're not looking at the pulse rates separately, because remember, we're only looking at the differences. So once we did our sitting pulse rates, our standing pulse rates, great. We forget about those numbers. We only care about the differences. So the population of all differences is what we are checking when we're checking for that sample size. This is a means test, so we are still using a t-test statistic and a t-distribution. So we've got our formula for our test statistic. And then naturally, I've got a couple of examples for you to look through. Just to give you some context on 22 and to talk about why this is a paired t-test. So in 22, you're investigating whether or not the express lane is faster than the regular lane at the supermarket. These students went in at 15 randomly selected times during the week. So the reason we would want to pair these data together based on time of day is because the grocery store is busy sometimes and not busy other times, right? So here, the time that they spent in the express lane versus the time they spent in the regular lane likely depends on how busy the supermarket was at that point in time. So these two times here are dependent, this one and this one are dependent on the time and the day that these students went to the supermarket. Just like these two down here are dependent on the time of day the students went to the supermarket. 23 is also a paired t-test. 23 also includes a question about a confidence interval and what we could infer based on our results of the hypothesis test and the confidence interval. As always, I've got some extra practice problems for you to try. Again, I encourage you to work these out on a separate sheet of paper and then compare your answers with the answer key. I think I've got a few here. Yeah, and then there might even be one more. So here we've got 1, 2, 3 extra practice problems with multiple parts for a paired t-test and paired t-confidence interval. As always, shoot me an email if you have any questions. Remember, we have office hours on Zoom. I sent that link via email on Thursdays at 10:30 in the morning. So hopefully I will see you then.